It's a great pleasure to be here in this program, and even a better pleasure to introduce the first lecture, 2-hour lecture by two of the organizers, Adri of Daalhuis and Christopher Howls. So they will be talking about Stokes phenomena from Dingle to exponential asymptotics. And if there are, this session is being live streamed on YouTube, and it is being recorded as well. So if you want to ask a question and you don't want to be recorded, please use either the Q&A or the chat function. You can type the question and I'll convey to the speakers. Finally, it was suggested to keep your cameras off, but when it comes to question time, it would be better. And if you want to ask the question unmuting yourself, it would be better if you could also switch on your camera so that we can see each other's faces, whether possible, of course. So with no further announcements, I would then pass on to Adri to talk about Stokes phenomena from Dingle to exponential asymptotics. Or Chris, I don't know who's starting.
I think I'm going first. Okay. Right. Thank you very much, Anna. Thank you, David, and thank you, Ines, for that introduction. So the lectures you're going to hear this week, not just in the few talks that Adri and I are giving, are going to give you lots of different gospels in terms of the subject. So there are many ways in doing the subject. You know, they've all got their strengths. Some have some weaknesses. And whatever we're going to tell you today is, you know, this is the way that we decided to or carried out some of our work. But as I say, there are many other techniques available. And so please have a look at all the lectures and don't just think that the one lecture course is the one that is the gospel truth for everything. Okay, so if you don't mind, I'm going to switch my screen off because you don't want to see my bald head as I'm talking to my iPad down here. But I'll just switch that off and then share my iPad, my screen. Okay, sharing the screen, iPhone via cable, share like that. Okay, can everybody see that? Yep. Okay, so stop video. Right. So the topic of this talk is an gentle introduction to Stokes phenomena from Dingle to exponential asymptotics. For those of you who were at John Chapman's talk the other day, you'll have seen some of this in that context. But we'll run through it again because there's the canon of work leads up to the things that we'll be talking about later on. Okay, so the things that we're going to cover today are basic introductions to Poincaré. We're going to look at some examples of area functions associated with that to introduce the Stokes phenomenon. That's going to then let us talk about optimal truncation and smoothing. We'll go into talking about universality of coefficients and then linked on to how you might improve the accuracy if you were interested in doing so beyond exponential accuracy. And this leads us into the idea of resurgence in general and in a basic form, not necessarily in the more sophisticated form that we're going to hear later on in the week. The next lecture will be about integrals, so I'll do some stuff on integrals and say how that briefly relates over to the Borel plane. The integrals are a nice geometric way of doing things and helps to explain certain things. We'll show how that leads on to calculating Stokes constants, either geometrically or actually algebraically as well. And then Adri will talk later about some parameter asymptotics, how that generalizes it, and also how things like nonlinear ODEs begin to complicate the whole thing that we're talking about here a lot more, but nevertheless, they can be handled. Okay, so let's first start. So what is exponential asymptotics? Well, it's basically the inclusion of initially, or in some parts of the complex plane, exponentially small prefactored terms in an asymptotic expansion. So rather than just have, say, an algebraic expansion here for a function y in terms of a small parameter epsilon, this, if you like, is a perturbative expansion. What you also are thinking about including are terms here which have initially exponentially small contributions you say e to the minus f of x over epsilon, where f is say real and positive, at least in one sector that you're interested in. We have k, which is a Stokes constant here, which may depend on the small parameters we'll see later. And you have some non-perturbative expansions here. In general form, you can also add to this. So in the nonlinear case, you'll be having terms here, which is say p equals 1 through infinity of p times this and k to the p. And this will be terms depending on p. And in other cases, you can have logs as well. But essentially, it's not being content with the simple algebraic or whatever gauge function you're using expansion. You also include some exponentially small corrections as well. The reason we look at this is because it removes ambiguities associated with the Poincaré expansions, as we'll see in a minute. It also resolves the confusion over the Stokes phenomenon, which we will also explain, whereby asymptotic expansions appear to change abruptly as the parameter is varied. If you're interested in numerical accuracy, it can be used to increase numerical accuracy. If you're interested in analytic properties, then it can also increase the range of validity of the approximations. It provides additional information to actually aid you if you really want to do rigorous work. And from a physics point of view, including the exponentially small terms, it's often got a very important physical meaning and that needs to be included. And actually, at the end of the day, it's not actually that much more effort to include these terms than if you can work out the perturbative expansion in the first place. So divergent series and asymptotic series, first of all, are not necessarily divergent. They can be convergent, but there's a long history of divergent series, which is the things we're going to be dealing with here. And that goes back way back. So for example, Newton was very keen to use the geometric progression expansion of 1 over 1 minus x, where mod x is greater than 1. In other words, where the thing didn't converge. And he derived results using that. One of the first big pieces of work on divergent series by someone detailed was Euler around the 1740s. And he wrote a whole treatise later published in 1760 on divergent series. And it was specifically looking at divergent series. So you can see he's got different examples here. Down here, he's got the ones that just add up, 1, 1, 1, 1, ones oscillating ones, and all of these types are there. But what in this talk, what he did do is he came up with 13 different ways of summing what you're going to see time and time again this week, which is the factorial over power form of a divergence expansion of this type. This led to actually a big argument with Bayes, as in Bayes' theorem, about how ridiculous this was, and kicked off basically 200 years of people arguing a lot about what the point of divergent series was and how they're alternatively evil and wonderful, and how you can do things with them. So in the 19th century, Cauchy provided the definition of convergent series, and so naturally analysts and a lot of mathematicians converged towards that idea that things should be expressed in terms of convergent series. And there was basically a distaste then for divergent series. They fell out of use, and people rejected them. And there's Abel's famous 1826 quotation about how they're the invention of the devil and it's shameful to base on them any demonstration whatsoever. Of course, later contradicted by Heaviside, who said, well, the series is divergent, so therefore we may be able to do something with it. Anyway, so there was this controversy going on, and ultimately in 1886, Poincaré came up with his definition of an asymptotic series. And Poincaré's asymptotic expansions, he says nothing in it at all about whether they're divergent or convergent. But his definition is of the following form, that if you have a function y of z, for z in some complex sector S of the complex plane, then let's suppose you pick your gauge functions to be powers, then essentially y of z twiddles this infinite sum of coefficients AR divided by z to the r, where mod z is tending to infinity in this sector. And what that means is, it means that if you fix a truncation of that series and you have a fixed capital N, the remainder has the property, which is the difference between the actual function and this truncated series, n terms in the series, that will be of order of the first term neglected. In other words, it's going to be less than or equal to a constant times mod z to the minus n. Okay, so this is a definition, and there's lots of theorems that follow from this. And as a result, you can actually use Poincaré asymptotic series you can manipulate them as if you're dealing with the actual functions of the operations, the simple algebraic properties of operations and integration and things like that. but it doesn't work for differentiation. So there's a slight fly in the ointment there. But nevertheless, that's possible. And this was a big breakthrough, because you can add two asymptotic series, and they also will be asymptotic as if you were adding the two original functions. So the advantages are that for Poincaré that you get a calculus of manipulations, that's fine. If you choose a fixed n, the first few terms numerically often give a relatively good approximation to y of z as mod z goes to infinity, at least in the sector that you initially fix you're interested in. And the other thing is the definition works for both convergent and divergent series. The disadvantages are, well, it's often difficult to prove that something is a asymptotic series. There's a lot of trees have died in trying to produce papers proving that things are asymptotic. R of n may not actually be small for all values of s within S. Why? Well, because you have to fix your n. And so you fix your n for all time, and then your z may be moving around in your sector, and depending on where it is in your sector, that may or may not give you a relatively good approximation to the function. We'll see that later on. One of the biggest problems, of course, is that it neglects terms which are exponentially small. So that leads to lots of ambiguities. So if you start off with your original function y, and it twiddles this particular asymptotic series here, if I add an e to the minus z to the left-hand side, well, e to the minus z has a Poincaré asymptotic series, which are all the coefficients are 0. And so essentially you add nothing to this right-hand side. So you end up with that y of z e to the minus z turns out to be asymptotic to e to the y of z. So exponentially small things are ignored. And so a particular asymptotic series is ambiguous as to whether it just obeys, it's a series for y of z or y of z plus, say, e to the minus z for mod z, for the real part of z greater than 0. So that's one of the biggest problems that led to a lot of controversies throughout the century after Poincaré. The other thing that is an issue is that it's defined for z in one particular sector, but if you move z into another sector that is different, then all the other things, as we'll see, can happen, and so you have to reset and rejig at that point. So it was widely adopted by analysts because it allowed people to start rigorously proving things. There was ambiguities due to these exponentials and other things over the next 100-odd years. And the reason that it does cause some problems is it actually, as we'll see later, it ignores the very cause of the divergence, which are distant singularities which give rise to exponentially small contributions. And so because it ignores those exponentially small contributions, it doesn't really cope with the Stokes phenomenon very well, whereby exponentially small prefactors may appear or disappear as the control parameters are varied. And that then leads to apparent discontinuous changes in asymptotic representations. And the first canonical sort of example that people look at, or some people look at here, is the ARAW function. So let's have a look at that now and introduce that problem, the Stokes phenomenon, through that. So here's a picture. Some of you who've heard me lecturing before would have seen this before, so I apologize for that, but it may be new to others. So here is a picture of a rainbow over Newton's birthplace, which is Walsthorpe Manor in Lincolnshire, a very flat area in the northeast of England, or in the east of England, sorry. And what you can see here are the rainbows over here, and there's a secondary bow here, a primary bow, and the things we're going to be interested in are these little fringes underneath the primary bow, which are called supernumerary fringes. Now, the thing was that in 1838, Airy, based in Greenwich, was the Astronomer Royal, and he was very interested in the idea of these fringes because as the Astronomer Royal, you have to use lenses, and these fringes will appear in lenses as well. So he wanted to be able to have a predictive theory for these fringes that come about in order to maybe control better to improve the optics of telescopes. So there were plenty of experimental results about to predict where, or to examine these fringes, but he wanted this predictive theory in order to work out how to control them. So the way that he did it, let's just turn everything black and white, is that if you have a rainbow crossing coordinate x as a function of the wavelength, then you fix the wavelength. then it turns out that the intensity of the waves, y squared of x, is given by where y is ai of x, what turned out to be called the Airy function, and that satisfies a second order differential equation here, d2y by dx squared minus x times y equals 0. So about probably the most simplest thing you could do to a constant coefficient equation to make it change. As we now know, because we can easily plot it, the Airy function is exponentially decaying for x greater than 0 and oscillatory with a power law decay on the amplitude for x less than 0. For the actual Airy function, it doesn't really matter so much what these are here, but for the actual Airy function, the initial data are given by these combinations of constants down here. So the problem that Airy had was he thought that experimentally he could sort of get this pattern, but he wanted to look and see how can I predict where, for example, these fringes are. So the point is that the Airy function here, the main rainbow, is given by it's not at x equals 0, it's given by this amplitude here. And then at each of these oscillations, the maxima and minima, because you square it to get the fringes, at each of these maxima and minima, you have these supernumerary fringes. So he wanted to compute where these supernumerary fringes were to check against his experimental results. So you can do this. You can provide the first leading order approximation in, say, the Taylor series expansion. And this is just a straight line here, which gets the tangent of the and the intersection at x equals 0 quite well. And you can carry on. You can get the cubic expansion, and it's not surprisingly, the red curve is a cubic. And then you can go further. And you think, well, if I add a quartic, maybe I'll pick up the first oscillation. Well, it doesn't work like that. Actually, this is the 12th order Taylor series expansion here, and you can see that it doesn't even get that first expansion. It's very, very good close into the origin, but it doesn't pick up that first fringe, the location of that first fringe. And that's therein we're getting to the problem, because remember, this is 1838. There's no Mathematica Maple computers or anything. This has to be computed by hand. So you need a way of doing that. If you go to the 13th term, well, you do get the, first of all, you get the turnaround here, but it's not in the right place. It's not accurate. It didn't agree sufficiently well with the experiment. And it's not until you get to the 19th order Taylor series expansion, 19th order polynomial, that you actually do get a pretty good fit for where it is. And so that's the problem, that essentially convergent series weren't really good at computing these. So essentially you had to then come along and wait, and then Stokes came along, and wrote down what's effectively the WKB expansions, and he had a one-term exponential expansion on this side, and he had a two-term exponential, a sinusoidal pattern on here, which accurately represented the got those fringes at exactly the right point. Of course, you'll see that obviously at x equals 0, there's a divergence, but you know the fringes are where they were interested in experimentally, so that was sufficient for what they wanted. So on the face of it, that's a really good thing. But of course, it turns out that those series are both, the Stokes' results are divergent, which causes if you take more terms in it, it causes a bit of a dilemma. However, let's have a look. Convergent series, which we're all taught at undergraduate level to know and love, basically numerically are often not very useful. So here's the Airy function, the convergent series of the Airy function here. And if you look at the number of terms, there's about 35 terms here, and you can see that convergent series tend to go up. The error tends to go up before it tends to come down. We know that the error has to go down for it to be a convergent series, or the term size has to go down, and therefore if it's an asymptotic series, the error will have to go down. But nevertheless, it's rising initially. So all this period here, you're wasting your computational effort, and it's not till you get back down to this level that you're actually beginning to get anything more accurate in terms of the number of terms than you started off with. The converse is true with the divergent expansion, in that this is the Stokes divergent series expansion for the Airy function, the WKB expansion for x equals 5, and you can see that the terms immediately go down, and that looks brilliant, and you're getting much better for the same number of terms, roughly, you're getting much better accuracy than you would for the convergent series. But of course, the thing then diverges again, and that's ultimately, if you take all the series in the terms, you get numerical contradictions, and the whole thing doesn't work. So this is again, you know, another dilemma, that a divergent series, nevertheless, for a finite truncation, gives you a very, very good approximation. The other thing that bothered Stokes for a long time was the fact that he had one exponential on this side, and he had two exponentials on that side. there was a singularity here, which meant that there was a border between the two, but he worried about how one exponential goes into two exponentials. Why do you get one vanishing if you go the other way, or if you walk from positive to negative, how do you get the other one being born? So this was the problem that vexed him for quite a lot of his career. From 1850, he wrote about 4 papers on this, going right up until 1902, when he just sort of did a retrospective of what he'd been doing. And so the issue that I think in the 1902 one, which is interesting for us, is that he said, as theta passes through the critical value, the inferior term, the exponentially small one, enters as it were into a mist, is hidden for a little from view, and comes out with a coefficient change. The range during which the inferior term remains in a mist decreases indefinitely as the modulus R increases indefinitely. So basically, this is him basically saying, don't really know why it works, but it does, so we'll just use it. So at that point, I will hand over to Adri, who will take you through a slightly more rigorous approach to that. So I'll stop sharing and hand over to Adri.
Okay, I also have to find my screen to share. So these are supposed to be the same slides, and I will upload them and probably in the second hour of this talk, so you can also have access to the slides themselves. So let me now explain how Stokes actually discovered the Stokes phenomenon for this particular example, the differential equation for the area function. So this differential equation is a second order differential equation. It has 2 solutions. The one of them is the area function. And for the second solution, typically you probably would write down the BI area function. But if you do asymptotics, it makes more sense actually to look at a rotated version of the area function. The natural variable for asymptotics is actually not z, but is this rescaled version of z, 2 over 3 times z to the power 3 over 2. And as you will see here in the asymptotic expansion for the area function, it arises naturally. It's the exponential of minus zeta, and the infinite series is also in powers of 1 over zeta. The coefficients un are given here, so they are a gamma function times a gamma function divided by another gamma function. So in total, it's a factorial over power behavior, so it's definitely divergent. And the asymptotic expansions, the first one for the area function itself, it lives in almost a full Riemann sheet. The only region that's excluded is a region around the negative real axis, but everywhere else, this is a very good asymptotic approximation. And the rotated version, of course, is then also almost a full Riemann sheet, but you rotate everything by 2 pi over 3. So the area function itself has as its main exponential e to the power minus zeta, and the rotated one has e to the power plus zeta. So along the positive real axis here, the area function is the recessive solution, and the second solution is the dominant solution. And the question that I want to answer here is what actually happens near the negative real axis. So what happens near in this sector here with the area function itself, with y1? So its asymptotic expansion is not valid there. But if I look at 2 different versions of the area functions, then they are valid there. If you take this function here, was already valid there because it lives between minus 1 over 3 pi and 5 over 3 times pi. If you take this other rotated version of the area function, where we rotate by 4 pi over 3, then that's also a solution for which its asymptotics also lives near this line. So I have 3 functions now, and we have a second order differential equation up here. So there must be a linear, the y1 should be a linear combination of these 2 solutions here. What are these constants a and k? Let's first focus on a, that's the easy one, because y1, this y1 here with this scaling of this rotating of 4 pi over 3, it has exactly the same asymptotic expansion as the area function itself. So those 2 functions, y1 and y1 times z times this exponential, have the same asymptotic expansion, and that expansion is actually dominant along this line 2 pi over 3. And that means that we know what the constant is. This constant in front of it has to be equal to e to the power minus pi I over 3, such that they are identical, the asymptotic behaviors along that line. So that's the easy one. The hard one, and that's the one that's the Stokes multiplier, is this red k. So in this talk today and tomorrow, you will often see a red k appearing. That's always a Stokes multiplier. And that's the object that we want to study. So we now know what this A is, and let's now focus on K. So this is my linear combination. And what is this K? Let's first start at the positive real axis. At the positive real axis, Y2 is the dominant solution, Y1 is the recessive solution, and this is also recessive. So K has to be equal to 0 along the positive real axis. Now let's study it along the negative real axis. Now the solution itself, the area function, is real valued, and this is a real valued differential equation. So along the real axis, the function has to be real. However, if you take these two, the dominant combinations of these two terms, then you get this complicated expression here for the first term and a similar expression for the second term. And these are complex valued, and for it to be real, the second term must be the complex conjugate of the first term, and the only way that that can be is when this k is equal to I. And that's how we can determine this k. But that also means that k is equal to I along the negative real axis, and k is equal to 0 along the positive real axis. So where has it changed? We're dealing here with differential equations, so everything is supposed to be continuous. But we have a constant here that switches its value. And Stokes realized that if you travel from plus infinity to minus infinity, not along the real axis, but you travel to it in the complex plane, then something funny must be happening. So if you travel along the half circle here, then somewhere this constant has to change. And his analysis went much deeper than anyone else, maybe for the next 150 years. He went into optimal truncation along this line here, and he realized that it had to be along this Stokes line here. So I'll do that in a moment, but let me first focus on what is actually the Stokes phenomenon in this case. It is the changing of this value from 0 to I. So we switch on an exponentially small term. So there is a switching on. This term wasn't active here, and it is active on the other side. And the reason that I'm focusing on that is that because if you would go to Wikipedia or some books on where they are supposed to be experts on asymptotics, they actually give this example here for the Stokes phenomenon as an example, a trivial example, but they call it an example of the Stokes phenomenon because the sine hyperbolicus function itself behaves like e to the power z when the real part of z is positive and e to the power minus z when the real part of z is negative. But in this case, there is no switching on of any exponentially small term. The only thing that happens if you cross the imaginary axis is that the two exponentials, who are both active everywhere, they just switch dominance. So this has nothing to do with the Stokes phenomenon. It's not a trivial version of the Stokes phenomenon. If you want to give it a name, then you definitely should never refer to Stokes, because Stokes definitely would never refer to this as a Stokes phenomenon. So the birth of an exponential is important in the Stokes phenomenon, and you really need divergent series for this thing to happen. And of course, in the sine hyperbolicus functions, there is nothing divergent. Okay, let me now continue with what Stokes did. So he wanted to make this switching on of the exponentially small term visible. And he also realized that optimal truncation exists for these divergent series. And you have to remember that this happened 50 years before Poincaré defined the Poincaré asymptotic expansions. So he was actually doing a lot of Poincaré asymptotics and then going deep into it way before anyone else. So as Chris just illustrated, these divergent series, the terms first decrease in magnitude. they reach a minimum, and then they have to increase the magnitude because the series is divergent. So that there is a smallest term. How do you determine the smallest term? Now, if you are close to the smallest term, then the terms are roughly the same size. And that's something that's very useful. So if you take the nth term and you divide it by the nth minus first term, then in absolute value, that must be approximately equal to 1. But this can be computed exact in this case. So this is the exact representation of the nth term divided by the n minus first term. And if n is large, then this is approximately n divided by 2 times zeta, absolute value of zeta. And hence, that's the optimal number of terms, taking 2 times the absolute value of zeta. And what is the size of this smallest term? So if you take this smallest term, we replace n by 2 times the absolute value of zeta, so we also have to do it inside these UNs. And then we use Stirling's formula for the asymptotics of the gamma function. Then you can get this result here. So there's some prefactor here that's not very interesting. You still have this e to the power minus zeta that was already in the area function itself. So the extra bit is this e to the power minus 2 times the absolute value of zeta. So this smallest term is exponentially small compared to any term in the divergent series itself. So this seems to be a kind of almost a contradiction here. Like, and how can it be that the smallest term is smaller than any term in the divergent series itself? And the reason for that is that you don't take a fixed n, you actually have to make n a function of zeta. But Stokes went one step further. I mean, this is the smallest term, the size of the smallest term. We have to switch on a term that is of size e to the power zeta. That's the object that we are switching on. When are those two objects of a similar size? Now, anywhere in the complex plane, this smallest term is much, much smaller than the object that we are supposed to switch on. So the only place where this can happen, where they are of the same size, is when the argument of zeta is equal to pi. So when zeta is negative, then this exponential is the same as this exponential here. And that is when the argument of z is 2 pi over 3. Now that is the way that how Stokes reasoned that the Stokes phenomenon has to take place there. But he went further, he also started doing numerics, because he wanted to make the switching on visible. So for that, he just took the area function, he took away the optimal truncated asymptotic approximation and divides by the behavior of the term that is switched on. And what you make visible then is the constant. And he was doing it for a particular value that I'll show you on the next slide, but let's first do it for when the absolute value of z is equal to 10. Then the optimal number of terms in that case is given in this formula here, so it's 42. And we write z as 10 times e to the power theta times I. And we compute this constant, which is now a function of theta, which for theta between 0 and 2 pi. And what you see there is that if you compute this constant, then it's 0 at the beginning. And then the imaginary part, that's the green part, switches from 0 to 1. But this is the imaginary part, so it switches from 0 to I. There's also a little bump in the real behavior, but that's not very relevant in this case. So what you see here is the switching on of the Stokes multiplier, this constant k, which is not a constant, as you can see. It depends on theta. And it switches on smoothly from 0 to I in the neighborhood of 2 over 3 times pi. So on one side of it, it's definitely 0. On the other side of it, it's definitely I. And close to it, it goes from 0 to I. In physics, often the people use that on the Stokes line itself, it's equal to a half. But this looks like an arrow function here. And this was the calculation that Stokes was doing. He wasn't doing it for 10. And the reason for that he wasn't doing it for 10 is because he couldn't compute this difference here, because in that case, you also have to be able to compute the area function very accurately for these large values. He was doing it for z equal to this value here, 2 times 3 to the power 2 over 3, which is approximately 4.16. Which is actually close to the value that Chris just showed you when he showed the Maclaurin series at the origin. And the reason that he had to do it for a relatively small value is because he had to compute the area function with its Taylor series at the origin. And that is just doable for this value. And he knew that he had to take 11 terms in the optimal truncated asymptotic expansion. So he computed this not for many, many values, but at least for a couple of values here. And he realized that the Stokes multiplier was 0, and for a couple of values here, and he saw that it was I on the other side. But the smoothing here is not as steep as what you saw in the previous case, because the value of z is quite a bit smaller. So that's what he did in this paper down here. And before I hand over back to Chris for a moment, I have an exercise that maybe you can do tomorrow, but I will actually use it in a moment. And that's actually an interesting integral representation that you can get from all the analysis that I've done so far. So the asymptotic expansion or the asymptotic approximation for the area function is given here, which lives in this large sector here. The connection relation that I wrote down earlier between y1, y2, and another rotated version of y1 is more symmetrically given here. If you combine these two results and choose a clever contour for Cauchy's integral representation for the area function, you can actually derive this, what we call Cauchy-Heine integral representation for the area function. And it's interesting because the area function itself reappears here. That's the kind of resurgence property that's relevant in this whole meeting at the Newton Institute. And this integral representation here, we have it in terms of z to the power 3 over 2, but as you know, that's not the most natural variable to do asymptotics. So this same integral, if you express it in terms of the more natural variable for asymptotics, that's zeta. And if you let tau be a similar value for the integration variable, then you can write it slightly nicer in this version here. And in this case, it looks more like a kind of Stieltjes transform of the area function. The reason that this is actually useful is because the area function itself is exponentially small along this contour here when you go to infinity. There's another exponential here as well, so makes it double exponentially small. And that means actually that you can actually play around with this integrand here and do a kind of geometric progression, which I will do in a moment. And another feature that this integral representation has is it has a pole here, or here, which one you don't know which one you prefer. And that pole, if you are forced to cross that pole with your contour of integration, that's exactly the Stokes phenomenon. So, but I'll give you more details later. Now Chris will take over again. I hope.
Okay, yeah. So that was the calculation that Stokes did. And then we've had Poincaré coming along after Stokes, deriving that. But essentially what happened over much of the 20th century following that was that analysts, applied mathematicians and physicists all sort of went their separate ways. I mean, this is a big paraphrasing of the case, but basically it came down to analysts focused on Poincaré analysis and rigorous proof. They had confusion and arguments over the Stokes phenomenon of divergence. Hardy actually went back in the spirit of Euler in 1948 and wrote a very good long text quoting in Greek, German, Latin, and I think French about divergent series. But that they focused on that area. Physicists, of course, in the meantime came up with quantum theory and field theory. The formal approach that they did using WKB methods and this type generally worked. The divergence of the issue wasn't, divergence of the series wasn't so important. Feynman worried about this, but never got as far as worrying, as coming up with a resolution. But in general, physicists used the Stokes phenomenon as a tool for essentially tunneling phenomena, but kind of ignored the divergence overall. Applied mathematicians carried on developing matched asymptotic expansions, multiple scales of this, and very practical methods like that, and carried on a formal approach that worked, maybe perhaps sometimes a bit of a black art in terms of experimental try it and see if it works approach. But in general, the divergence of series was ignored by applied mathematicians as well, and from that point of view. There were many other people involved along the way. So Borel, of course, as you'll hear later, 1899 came up with the Borel summation. Watson and people like this worried about factorial over power series and various of that type. And then, as we'll hear later in the week, Ekal came up with an incredibly comprehensive theory in the late 80s. But I just want to touch on the work of Robert Dingle, who was a solid-state physicist. And we've seen in the Airy function the factorial over power behavior, and what he advocated was that actually that factorial over power behavior was much more universal in the late terms of asymptotic series, in whole classes of them. And he justified that using the Darboux method, which is, to paraphrase, basically looks at a singularity, the effect of a singularity on the higher order terms through, say, differentiation. And that ends up compounding to give you, with the successive differentiations in recurrent series that are generating those terms, gives you the factorials over the powers that you are interested in. And he used Borel summation. We'll see that in a minute. So he published around 6 papers on converging factors in the late 50s, and realized that divergence and Stokes phenomenon then are intimately related. And that his argument was that divergent late terms somehow encoded the information. Converging factors, he then proposed converging factors, which were ways of taming the divergence of those series that actually simultaneously included the Stokes phenomenon as well. So his work was far from rigorous and largely ignored by rigorous analysts, but led in part to a lot of the work that you're seeing over these lectures. So in general, as we've seen already, we have the series we're dealing with are going to be divergent, and typically they'll have factorial over powers, and they'll have the factorial here, that these can be multiples of R plus mu. I've just put it in that form, but the idea is that the powers on the bottom are not necessarily a direct function or a direct value of Z, the large series expansion. They could be a function of them, and those were what Dingle called his singulants. And as we'll see later, they correspond to difference in heights between saddles or distances between singularities in the Borel plane. And the whole purpose of this is now, as we've seen for Airy, that you can actually then substitute in Stirling's approximation for the gamma function, and that will then show you that you can end up with finding that the least term is always e to the minus mod f, effectively of this order over mod f. And that gives you the opportunity to, if you believe this is an asymptotic expansion, to sum to get exponential accuracy. And that then is the general idea of Dingle, that this, what we've seen in Airy, was a much broader approach and allows us to come up with a more comprehensive theory. And Adri will now go through that and explain that in a bit more detail.
Sorry, I was muted. There will be a little bit of repetition in this presentation, but now instead of looking at the slightly more complicated asymptotic expansion for the Airy function, let us now actually move to the simplest asymptotic expansion, which actually is hinted by this statement about two series. One is convergent, one is divergent. And that's this sum here, n factorial divided by minus z to the power n. That's the cleanest the divergent asymptotic expansion. And if you replace the factorial by an integral representation, and if you then interchange summation and integration, then you obtain an integral representation for it. And probably later this week, people will start calling this the Borel transform of the divergent series, the Borel Laplace transform of the divergent series. So that's the object that I want to study now. And let's give it a name. Let's call it f of z. And it's actually a known function. You can either express it in terms of an exponential integral or an incomplete gamma function. So it's a function that we can compute everywhere. It's a solution of this second order homogeneous linear ODE, for which the exponential e to the power z is a second solution, an exact solution. And finally, connection formulas are very important in these presentations. And this is the connection formula. If you go with f of z, one Riemann sheet, higher or lower, you switch on 2 pi I times this exponential. And that just follows from the pole that you can see here. So there's nothing deep here. The nice thing about this integral representation that we have here is that you can just actually expand this 1 over t plus z in a geometric progression. You get for free the asymptotic expansion, but you also get an exact representation for the remainder. And as you just saw, this is a bit what we will call a special case of Dingle's determinants. Like with the area function example, we can look for the smallest term. So 1 is the nth term divided by the n minus first term, approximately equal to 1. Now in this case, it's even simpler. You get exactly that it's n over absolute value of z. So the optimal number of terms in this asymptotic expansion here is absolute value of z. And the size of the smallest term in that case is given here. So it's a prefactor times e to the power minus the absolute value of z. Now, why is that relevant? It's relevant because if you compare it with the object that is supposed to be switched on via Stokes phenomenon, which is this extra term in the connection formula, e to the power z. So when is e to the power z roughly equal to e to the power minus the absolute value of z? Only along the negative real axis, so that has to be the Stokes line for this example. And we can do exactly the same as what we just did for the area function and study the switching on close to the negative real axis. So again, we take the remainder for this divergent series, f of z minus the optimal truncated divergent series, and plot it. So this is the remainder divided by 2 pi I times e to the power z, and we let z be equal to 20 times e to the power theta pi I, and we just check where is this function switched on, and close to the negative real line, you can see that the value goes from 0 to -1. Notice the minus here. So I'm not trying to cheat by making it +1 or so. And this is the real part of this switching on. You could argue, so where is actually this Stokes phenomenon happening? Because I'm not just plotting the function itself, I'm subtracting here actually this polynomial. But this polynomial itself does not have any special behavior near the negative real line. So this object definitely will not do this, what you can see here. So this switching on here is really hidden in the tail of this divergent series here. So all the terms that we are not subtracting. So in this case, the Stokes phenomenon is just the switching on of 2 pi I times e to the power z. And it can actually be described by an arrow function. And that's actually Michael Berry's important contribution in 1989. But he, for the first time, actually showed that it was an array function. And so this was also in the talk by John Chapman on Thursday. And he also derived it, and he did it the way that Berry did it. This representation that you can see here is actually what the mathematicians did afterwards, after Berry. And it's much more uniform, but still looks very similar. So this behavior that you see here, it's approximately equal to -pi I e to the power z times the complementary area function of alpha times this square root of n over 2, where alpha is defined here. And most importantly, alpha is 0 when z over n is approximately -1. And this approximation here, which is uniformly valid in large sectors in the complex plane. In the exercises for tomorrow's workshop, one of the exercises is for you to actually derive a proper proof of this approximation here. Okay, so this is maybe a good motivation to introduce now hyperdeterminant functions. So that are very similar functions to this function that we just had, the function capital F. But these functions have their Stokes phenomena in other directions. So hyperdeterminant functions are the simplest functions incorporating a Stokes phenomenon, but in a particular direction here. The argument of sigma times z is equal to pi. I mean, that's the more convenient way of writing it down. The functions are defined here, so we integrate in a particular direction to infinity. There is a pole here. There's again a simple exponential and a simple power there. And if you look at the asymptotic expansion for this, then you obtain again an expansion here in terms of factorials divided by powers. But it's not just z to the power n, there's also an n involving these bits here. The remainder, in this case, can again be expressed in terms of this f1 function. So if you start with f1 at a, you get then f1 at a plus n with an extra z to the power minus n. But that's just because we did use a geometric progression in the original integral representation to obtain this result. The other important feature that this function has is that its connection formula. If you go to a different Riemann sheet, then you switch on again 2 pi I times an exponential, and in this case, an extra z power. So if you would have taken in this example, a is equal to 1 and sigma is equal to 1, then you're back to the function that we just had on the previous sheets. But these are the approximants that I want to use in the next couple of slides. And again, let me just emphasize that these functions do incorporate the Stokes phenomena, and they are the simplest functions having a Stokes phenomena. And they have the same arrow function smoothing that you saw on the previous page. It's the same alpha that we have here. And so again, you get an arrow function times the object that is supposed to be switched on. For those of you who don't know the arrow function very well, the complementary area function goes from 0 at plus infinity to +2 at minus infinity. So if you multiply this times 2, then you get exactly this term here. And another reason maybe for some of you to actually have that you should be interested in this hyperdeterminant function is that here is an alternative integral representation given here. And this is more a kind of Borel, an integral representation that plays an important role in Borel analysis, because as you can see here, it's just a Laplace transform of a simple singularity in the Borel plane. So at the moment that you do all your analysis in the Borel plane, then this integral representation might be relevant. But for us today, we use actually this version of the integral representation. Okay, let's now see how we can use it in case of the area function. So for the area function, I gave you an exercise a couple of slides ago, and to actually derive this integral representation here, which did contain the kind of resurgence, because it contains the area function in terms of itself. It has this simple Cauchy kernel here, 1 over zeta plus tau. It holds in this particular sector. And at the moment that you plug in a geometric series, so if you expand this 1 over zeta plus tau in a geometric series and truncate, then you get an asymptotic expansion in powers of 1 over zeta. But we already have an asymptotic expansion for the area function. It's given up here. And asymptotic expansions are unique, so it should be the same asymptotic expansion. And in that way, you obtain also an integral representation for the remainder, an exact integral representation for the remainder. So it's roughly the same integral that you see here, but there's an extra tau to the power n here, and zeta to the power minus n factor up down there. And that's interesting, because this is an integral that we can actually estimate. If you integrate from 0 to infinity and you have an area function, the area function is well behaved along the positive real axis. So this integral representation here for the remainder, you can use to get sharp error bounds. In this analysis here, there's actually nothing very complicated, but these type of integral representations and these type of analysis of the remainders, they are actually new. People were not doing that before the 1990s. And now with all this machinery, we get suddenly sharp error bounds for many, many special functions. And in a couple of weeks, Gerben Nemes will talk about this machinery and how to obtain sharp error bounds for many special functions. But in a moment, you will also see another example. But how can we use this? So this exact remainder that you can see here, if you're now going to look at, in the case that of the smallest remainder, that means that n is large. If n is large in this representation here, then we have a tau to the power n. Now, where does tau to the power n have its maximum? Now, that's at infinity. And that tells you, if you know anything about integral asymptotics, that you should expand one other part of the integrand at that special point, in this case, infinity. And what we do here is we take this area function here, and this tau to the power n tells us that we have to expand this area function at infinity. But that's exactly the asymptotic expansion that we have here. So if you plug in for the area function its own asymptotic expansion, then we get a re-expansion for the remainder. So that's all we're going to do to obtain a re-expansion for this remainder. Replace the area function by its asymptotic expansion. And that means that you get an extra exponential, you get extra powers, but if you plug them in, then you get exactly this expansion here. So the coefficients are not special because they are the coefficients that we take from there. And actually there's nothing new in this representation except that the function that we expand in here are not simple powers of zeta anymore, but these are the hyperdeterminant functions. So another way of writing it is actually in terms of the function that I defined on the previous slide. And this is a re-expansion of this remainder when n is large. And the nice thing about it is, as I just mentioned, you don't have to compute anything new. There are no new coefficients that you have to compute. And this re-expansion, because it's in terms of this f1 function, they do incorporate the Stokes phenomenon. So the original asymptotic expansion here was valid for the argument of z smaller than pi, because we did not, this asymptotic expansion itself does not incorporate the Stokes phenomenon. And at 2 pi over 3, when the small exponential was switched on, and at the negative real axis, that small exponential became dominant again, and that's why we have to stop at that moment. But at the moment that you optimally truncate this expansion and re-expand, then actually you get a result that holds in the larger sector. And that shows you that these re-expansions are also an interesting analytic tool. And here's another way of actually looking at the same re-expansion in terms of the sizes of the terms. If you start with the original expansion and we take an optimal number of terms, so we sum up to the smallest term, and then we stop with this expansion. So that is that we take n as 2 times the absolute value of zeta, and then we re-expand in this new expansion. Then this new expansion here again is divergent, it will go up again. So we can truncate at an optimal number of terms, and that is in this case half the previous optimal number of terms, that is then the absolute value of zeta. And then you have to stop, but what you can see is that you have a much better approximation. So this is the sizes of the terms, but in asymptotics often the sizes of the terms are approximately also the sizes of the remainders. However, when Frank Olde and I were actually looking at this, we also realized that you can also look at the remainder, not just as first as a function of m and then as a function of m. You can also try to optimize this simultaneously as a function of n and m combined. And surprisingly, you can actually do better than what you saw here. If you take twice the optimal number of terms in the first expansion and then 2 times zeta in the re-expansion, then actually you get a result that is double exponentially small. So if this is of the order e to the power minus 2 times the absolute value of zeta, then this is e to the power minus 4 times the absolute value of zeta. And if you're a mathematician and you see this re-expansion once and you realize that this here is again a divergent series, then of course you can imagine that you do it again and again and again. And what you get in that case is a hyperasymptotic expansion. It's now 3 o'clock. I think this might be a good time to have a little break. And then I will continue with a few more slides after that before Chris takes over.
Adri, there's a question on the chat.
Okay.
Would you like to answer it now?
Yep.
Okay, so it's a question that is asking the following. So does this, so it was regarding page 59, 60. Does this mean that the Stokes phenomenon is simply a product of the multi-valuedness of the functions? In other words, they are single-valued functions on a Riemann surface?
Now, some people argue that in these approximations, for example, the one that you see here, then the area function itself is an entire function, whereas the asymptotic expansion it is not. Clearly, you see a z to the power a quarter, and this zeta here is also z to the power 3/2. So there is definitely a mismatch in multivaluedness, and some people argue that has to be the reason. And as far as I know, that seems always to be the case. And another issue is that one of the exercises that I set for tomorrow is that if your asymptotic expansion, if this one here would be a proper asymptotic expansion on the full Riemann sheet, so suppose the powers would have been just clean powers of z to the power n, then the asymptotic expansion will actually be convergent. And hence you won't have a Stokes phenomenon. I hope that answered the question.
I think so. And I believe there's no more questions for now. So let's go for the break.
Yep, 5-minute break.
5-minute break.
On different sheets. But still, there's a mismatch on the Riemann sheets, yes. And the first question, how do you compute the asymptotic expansion? I mean, if the question is how do you derive it, then one way is either you can derive it by just trying to plug in the WKB expansion in the differential equation, or you just use the integral asymptotic. So there are 2 ways of getting it.
Okay, we should resume, but there's another question. Sterling's expansion is also a founding object of divergent theories and resurgent theory. Will you treat it?
Yep, I do it in a moment.
Okay, so a bit of spoiling.
Yep.
Okay,
Okay, I'll
hand over
share my
to
screen
you.
again. Okay, so what I've covered so far, maybe we can summarize it on this slide here. If you have a problem that has, say, two divergent series that are given here, this is for asymptotics when Z is large, and the dominant behavior is given by these exponentials here, e to the power lambda 1 or lambda 2 times Z. Then, and you have divergent series like this, then typically you can plug it into your problem. If it's a differential equation, you just plug them into your differential equation and you compute the lambdas, the mu's, and all the coefficients. It can also come from difference equations or integrals, or even more complicated problems. But let's for the moment assume that we have two of those formal solutions that live in these large sectors. And at the same time, we have connection formulas. So in this case, the question was just about Riemann sheets. Let's really look at in this case, what happens if you move to the next Riemann sheet. Then in these connection formulas, one of the constants was easy, as I illustrated with the area function, that was the coefficient A. And the other one is just a multiplier that we don't know. Typically for differential equations, you don't know that multiplier. You know that it exists, but you don't know what the value is. And let's assume that we have a problem where we have two of those connection formulas, one for W1 and W2. Then you obtain, either by using Cauchy-Heine techniques that I just at least illustrated that they exist, I haven't given you any proofs, or maybe via Borel transforms, you can get the following two results, that the coefficients, the late coefficient, that is when S is large, in say for the first solution, when J is 1, you can express it in terms of gamma functions divided by powers, where this is the difference in the exponentials that we have here. But it's the same coefficient, so it's the coefficients of the second solution. That's the resurgence part. And so everything in here is known. There's nothing new there that you have to compute once you know all these things, except typically we don't know what your Stokes multiplier K1 is. But since everything is known on the right and the left-hand side, you can use formulas like this to compute those Stokes multipliers. So you can take S as large as you want. If these coefficients are easy to compute, you can make S very large. You should also take not just one term here, but you should actually take an optimal number of terms there, which I actually give in this paper down here, 1998 paper. And then you get extremely accurate approximation for the Stokes multipliers. However, at the same time, you also get re-expansions for the remainders. If you truncate this after n terms and say n is optimal, then you get for free an expansion in terms of these hyperdeterminant functions that I introduced a couple of slides ago. The coefficients are again the same coefficients. These are the coefficients of the second solutions. There is some prefactor here, but everything is known. And in the meantime, we are able to compute the Stokes multiplier from the previous result, and hence we get a re-expansion that will incorporate the Stokes phenomenon. And this is just a case of a problem where you have two formal solutions. If you have more of them, say you study an nth order differential equation, then that's given in this 1998 paper. Now, what seems to be crucial here is that the connection formulas are out of this form here, and that suggests that you need some kind of linearity. So does this still work in nonlinear problems? And the answer is yes, but you won't have any connection formulas anymore, but you will have trend series expansions. And tomorrow I will give an example for panel of A1 where you can do all this analysis for panel of A1 using trend series. Okay, two final examples from me for today. One of them is actually, if you go back to this previous slide, this result that you see here for the late coefficients, a special version you can get for in case of the confident hypergeometric function, which are solutions of this second order differential equation here. They are in terms of Kummer U functions. So the details are not important on this slide here. The only thing that I want to show you is that this expansion for the late coefficients gave rise to this final result on this paper here, on this page here, and that is that this quotient of gamma functions when S is large has a very beautiful asymptotic expansion with simple coefficients that's given here. And this is the gamma function of S minus R. We call this inverse factorial expansions. But the coefficients are very simple, and they just come from doing this type of analysis that you saw on the previous page for the solutions of this differential equation. Because this object here is a special version of the coefficients of this W1 function here, and the late S behavior of it is in terms of the coefficients of the second solution, where you see this B minus A, which also appears here, and the Y minus A appears here. And in the 1990s, when people started working on exponential asymptotics, suddenly 3 people wrote roughly the same paper where they derived this expansion. It's a beautiful, simple expansion. And the final example that I do today is the Stirling approximation. And that's probably the most famous asymptotic expansion. And Stirling was a mathematician in Scotland. And actually, if you ever come to Edinburgh, can show you where he is buried. It's on this graveyard here in the city center of Edinburgh. And funny enough, he is buried. So the person who probably is related to one of the most famous asymptotic expansions is buried on the same graveyard where one of the maybe most famous people in convergent expansion, and that's Maclaurin, about Maclaurin series. So they're buried on the same graveyard. And it's mentioned actually on here that he's actually a mathematician, but as you can see here in the middle. Okay, let me now move to the Stirling approximation and exponential asymptotics. So when Z is large, the Stirling approximation in this case is given here. The coefficients are well known. We have recurrence relations for them. And the terms that if you plot them in the expansion, so that's Gn divided by Z to the power n, they are plotted here. And you see a little difference between even and odd terms. And that will be relevant on the next slide. This is a divergent expansion. It's a very famous expansion. However, it's known for a long time, but there were no good error bounds for this. For the logarithm of the gamma function, it has also a very simple asymptotic expansion. And in that case, we know error bounds for a long time. But for the gamma function itself, there were no good error bounds in the complex plane. So the first error bounds were derived by Bill Boyd in 1994. And he was using the machinery that Chris Howls and Michael Berry introduced in the years before that. And Chris will talk about it in a moment. The optimal number of terms in this expansion is not Z, like in the previous case. It's actually 2 pi times Z. And that's actually very interesting information. I mean, you can actually spot it in this case. This is when Z is equal to 5. And then roughly 30 or 31 terms is the optimal number of terms. But it also explains why if you use this formula, which is for Z extremely large, if you use it for Z is equal to 1, you still get a reasonable approximation. Because 1 times 2 pi is 6, and 6, of course, is very large. And if you, in this example that you see if a Z is equal to 5, if you then use an optimal truncated approximation, then you get more than 14 digits in your approximation. So you get a very good approximation. That's also illustrated in this picture here. Now, what's the connection with exponential asymptotics and resurgence? Now, that's given on this slide here, and also the error estimate. For that, it makes more sense not to study the gamma function itself, but actually gamma star, which is the gamma function, but take away the dominant asymptotic behavior. So gamma star has just this infinite divergent series approximation, but if you truncate it, then we call the remainder Rn. The difference between gamma and gamma star, one difference is also that gamma itself has only poles in the complex plane, where gamma star has a branch point at the origin, and you have to take the negative real axis as a branch cut. In his paper in 1994, Bill Boyd also did obtain a new integral representation for this function gamma star. It's in terms of itself, so on the first hand you might say this is completely useless. However, this is useful because again you have this beautiful Cauchy kernel in here. And also we integrate here along the imaginary axis, and this is the negative imaginary axis. And along those lines, this gamma star and the gamma function itself, we know we can control that function very well. We have very sharp bounds for that function along that line. The way that this formula was derived in the paper by Bill Boyd was using the heavy machinery that Chris will introduce in a moment. However, you could also have obtained the same result by just using this resurgence of the disconnection relation. So that's the gamma star function on one Riemann sheet in terms of the previous Riemann sheet. If you combine this with some clever Cauchy integral representation, then you can also get this integral representation that you see here. Now, why is this a useful result? Now, especially again, because you can just expand this 1 over z minus w in a geometric progression, and then you get an exact representation for the remainder. So all that happens is that you get an extra w to the power n here, and z to the power minus n in front of the whole thing. And that's the representation for the gamma, for the remainder Rn. But because we can control gamma star along this imaginary axis very well, we have very nice bounds for it, you get very sharp error bounds. So that's the one that Bill Boyd derived in 1994. It might look complicated, but actually it's not that bad. There's a gamma function of n is just the number of terms that we take. There's the Riemann zeta function evaluated at n, but that's also a simple, relatively simple function. And it's a very sharp error bound. We can do slightly better, and that's what Gerger Nemes arrived not too long ago. And that's actually an error bound in terms of the first two truncated terms. So you stop after n terms, and then you can show that the remainder is less equal than the sum of the next two terms. And maybe you think that's a little bit of an overkill that we have two terms there. Why is it not just the gn divided by z to the power n? And that has to do with what you saw on the previous slide, that there is a difference between even and oddness here. So at the moment that you include both of them, and then at least you control that bit. So this error bound here is even simpler than the previous one, and it's obviously sharp because you have an expression in terms of the first neglected term. Because we multiply it times 1 in this sector here, and you have to multiply it times something else in the remaining part of the sector. So that's all I want to say for the moment about the Stirling approximation. And now Chris will take over with integrals.
There's just, sorry to interrupt, there's one question in the chat.
Okay.
Would you like to answer it now?
Yeah,
in Q&A.
Mm-hmm.
This methodology of determinants and then re-expansion of remainders, is it primarily used only if you have access to integral representation?
No, so far we haven't used any integral representations yet. We created ones, but all of them were created by just using asymptotics. In none of these examples, I did start with an integral representation.
Actually, it was the differential equations.
And I will do tomorrow. I will show that for panel of A1 you can do the same. You also get an integral representation for the remainders, and can do optimal truncation, computing Stokes multipliers, and also do re-expansions without using any integral representations, because the area function itself doesn't have any simple of the area function. I mean, the panel of A function itself doesn't have any simple integral representations.
Another question popped in just 1 minute ago. Could you please elaborate on how connection relations are obtained? Is there a general strategy to follow, or do they have to be derived on a case-by-case basis?
The latter. Depends how complicated your problem is. So typically what you do is you just plug it, you just try something. If it's a complicated problem, then you might say you try your original function and you add something extra and see what happens with that something extra. Tomorrow again, I will illustrate that a little bit for the panel of A.
No further questions for now.
Okay, Chris, take over.
Okay, so Adri's spoken a lot about differential equations approaches. I just want to run through here a basic original approach for how the Stokes phenomenon and asymptotic analysis and exponential asymptotics fits in for integrals. Now, the reason for doing this is because there are some nice, pretty pictures that you can draw, and so a geometric approach to the calculation. But it also is sort of effectively an introduction to Borel plane analysis, which other people will deal with. And essentially, the same techniques I'm showing you here also work in the Borel plane, albeit with a shift to a different dimension. Okay, so what I'm going to do here is I'm just going to consider some simple integrals. This is just a 1D integral here. Later, you'll hear how to do multiple integrals as well. But essentially, there's a function, an integral, which is of g of z e to the minus k f of z. So f and g are initially, that can be relaxed later, analytic functions. And k is going to be our large parameter, or mod k is our large parameter, but k can also be complex. So k, for example, this could be a Fourier type behavior here, or a Laplace type behavior if k was real. But theta k is going to be in some range. We'll keep it, say, 0 to 2 pi to start off with. And then the idea is that the contributions to these, the most important contributions to these integrals will occur around the saddle points, which are, in this case, let's assume that they are simple saddles. We can generalize later, but essentially a simple saddle will be where the derivative of f vanishes, and we'll assume that these are isolated simple saddles, so that they're not coalesced, so that the second derivative doesn't vanish. The notation is that f of zn of these saddles is f sub n. Okay, so that in general, there's going to be these saddles throughout the complex plane. I've drawn a couple here, and then we're going to integrate over the steepest paths, passing across these saddles, running between asymptotic values v1 and v2, or any choice of values that you want. The values, of course, are where the real part of f, k times f of z, is positive, so that the exponential then decays along those paths. Now, this may not be how your original contour is. Your original contour might be between minus infinity, infinity, and then you have to deform locally using Cauchy to get that. We'll look at an example of that later on. But essentially, we're going to be looking at the asymptotics now of k going to infinity. So this is a physics type thing here. If I wanted to be mathematical, I would put I would have 1 over epsilon in the exponent. But let's do it from a physics point of view. So it's a mod k going to infinity. But in what follows, that limit isn't actually needed. We're not really putting k to infinity, mod k to infinity. It can be any finite number as well that you like. So an example of this would be, say, the Pearcey function. So the Pearcey function here is given by a quartic exponent with z to the 4th, z squared, and a z with coefficients y and x. And this is a canonical catastrophe integral, which you can find in the digital library of mathematical functions. And it essentially, if I plotted this as a function of x and y, you get a pattern that looks like this. It's this oscillatory pattern here. The red line turns out to be where these saddle points coalesce. That's the caustic, the so-called caustic, the bright spot. As you move from across this red spot, locally as you come in across this spot, you actually got an Airy function. You can see you've got oscillations, a big rainbow, and then it decays. And so this is, if you like, a two-dimensional version of a rainbow. And this is part of the fact that it's a hierarchy of all the catastrophe integrals. And this is essentially the close-up of the coffee cup caustic here. And this is I found in my kitchen yesterday a Newton Institute mug, which I got my coffee cup caustic from there. I don't have to give anyone a credit for that photo. That's my own one. But anyway, essentially what the saddle points of this Pearcey function are, there's going to be 3 of them, and they will correspond to the 3 rays that you can get through any particular point in space that generates that caustic. So the saddle points here are where I differentiate. So you've got to solve a cubic. There are 3 possible rays for each point. The Pearcey function initially is running from -infinity to +infinity, but we're going to deform that in a minute onto paths of steepest descent through the valleys where the real part of kf is greater than 0. Now, depending on the parameters x and y here, when we do that deformation, we're going to have a chain of steepest paths which are going to pass over different linear combinations of those saddles, and they may then not just run between the valleys closest to -infinity and +infinity on the real axis, but they may take excursions running into intermediate valleys as well. So let's look at that now, and this will take some time. Sorry, it's a big picture, but essentially what have I got here is this is the original contour of integration red, and I'm plotting in here. This is the in real part of z and imaginary part of z, and then the green, the light green are the hills where the real part of e to the minus kfz gets large, and the black areas are the valleys where e to the minus kfz gets tends to 0. So essentially, this is just this integral along -infinity to +infinity is just on the borderline of convergence. So the first thing we do is just tilt it by a Cauchy, and then checking at infinity, the little bit of extra, the integral vanishes along this region here. We can then deform it to this straight line there. And then finally, when we put the saddle points in for a particular value of x and y here, 1 and 2, you find out that what happens is that you get 3 saddles at these points here. And then if you want to go between the value v1 and v3, which is where you've got to end up to get the Pearcey function, you'll go through this steepest contour here. When you do the path of steepest descent, that's where the imaginary part of k times f minus the value at the saddle point equals 0 from analytic behavior. And you will then end up going along that as the steepest path in that way. So that you end up going from -infinity to +infinity just between the value from v1 to v3 along that bendy path there. These are easy to generate either from flow equations, which you can write down, or from just plotting the contour plots for the imaginary paths. So if we pick another value of x1, we do exactly the same thing. We deform, and then essentially now we have the 3 saddle points in this case. But now when we look at the steepest paths, you see that the steepest path across this first saddle from v1 actually ends up makes an excursion into v4 before coming back to end up at the valley v3 there. So in that case, you can see what happens. You're now going to get 2 contributions from a saddle point expansion to your integral in your asymptotics, whereas in the previous example, you just had 1. So something has happened between here. You've picked up an extra saddle point contribution. You've had a Stokes phenomenon, basically. The next example then is when I'm on with x equals 0 and y equals -3, and you do exactly the same thing, but in this case, you see that you've got an excursion from v1 here to v4. v4 then comes down to this saddle point here before going into v2. And then you make this excursion again to this third saddle point of v3. So in this case, for this particular parameter, the values of x and y parameters, you've got then essentially 3 saddle point contributions. There's a chain of 3 contributions you have to take into account. So again, another Stokes phenomenon has occurred between the previous case and this one as well. And so if you then plot that in the xy plane, this is what you get. And essentially the situations I've been looking at are we had this was the first one, this was the second one, and this was the third one. And when you do a little bit more analysis, you can see that you get on this cusp shape down here, this is the bifurcation set on which you get 2 or more of the saddles coalescing. And so this is given by where the first derivative and the second derivative both simultaneously vanish and give you 0. And that gives you an elimination, you can eliminate z and you just get a function of x and y. It's basically x squared goes like y cubed there, up to coefficient there. And on the bifurcation set, you can see here that what happens is you get a coefficient, you get a coalescence of 2 saddles. And so in this case, you get the saddle, you would have to take a path like this, and you get a dogleg path in order to get those contributions. And you can see, whereas in the simple case, you just go smoothly through the saddle, when you've got two saddles coalescing, you get a more complicated local structure, and you have to do, as I say, a kink in the path there, and you get a dogleg. But that's what happens on the bifurcation set. On the red line up here, which you can calculate as well, is the Stokes line. And on that Stokes line, you see that what happens is, whereas below the line, you get just one contribution from there. Above the line, you're going to get two contributions from here, from the two saddle points. And you can see that exactly on the line, what happens is you get the two saddles joining precisely, and then you get a 90-degree turn for a dogleg there going off. So you get 1.5 contributions, if you like, of your critical points on that line. And it's symmetric in this case, and you can see on the other side. So essentially what happens as you vary x and y, and as we'll see in a minute, k, you can end up with different types of contributions occurring, and you will end up with these Stokes phenomena. The purpose of looking at it from an integral point of view is that whereas in Adri's explained things in terms of connection formula, in this case, there's a very nice, in one dimension at least, there's a very nice geometrical way that you can see what happens, that you can see the connectivity of these saddles change as you go through a Stokes line. You get this 90-degree dogleg behavior of the contour. Okay, so another thing is that we're going to look at, it's important for what follows, is if you look at theta k, we've thought of theta k as actually being just, say, 0 to start off with. But if I change it by a value 2 pi, what happens? Well, as theta k changes, the values are going to change, because that's where the real parts go, k times f and z go to 0. And also the contours will change as well. And so if you look at a particular steepest path through the saddle point n, say, and you change it by 2 pi, if it's a simple saddle, then you end up reversing the orientation of the contour. So let's say that I start off with this particular case. This is for x equals 0, y equals -3. And here is my contour that at the steepest path is going through here. Let's just worry about just this first integral. We won't worry about the contributions from the other saddle points to start off with. What I want to do now is I want to then let k vary. And if I let the phase of k vary, so I've got the phase of k up above, you'll see that as it varies, you can see that as it varies, the contour rotates and along with the values. So the red line is what it was at theta equals 0. But for every other intermediate value of theta, theta k, you can see that the contours are going to change. Now, if I can stop this thing at one point, yes. What I can do is, if I take it now round to theta equals, come here, pi, whoops, pi, and stop it if I can. Come on, 29.5, come back. There. You can see that more or less the contour has come back to itself. In all the rotation as it's gone around, it's come back to itself, but it's actually just made an excursion of pi. So it starts off running from the top left to the bottom right. Then as it goes forward, it starts to rotate, it rotates, it rotates. And if you carry on following the contour around, it ends up back there when theta equals pi. And then fully as you go around to 2 pi, it comes back again. And so what you've got is you've got a multi-value function of k. So in what follows, it makes sense to strip out an appropriate power of k, k to the 1/2 here, that makes this function here, Tn of k, this is single valued in the phase of k as you rotate it. And so we'll do that. This is a bit like Adri did with the gamma function, is you strip out the nasty bits in front. And I've also stripped out here, if you like, the exponential that you would have in front coming from the saddle point as well. So that's exactly how Adri did it in the gamma function. And now I'm going to look here, because this expansion is going to be algebraic in form. So what you then do, which is standard steepest descent method. So here I've plotted in the complex Z plane. Here's my steepest path going through the saddle point at Zn. You do the standard thing, which is you set u, or it could be u squared, but I'm going to use u here, to be k times f of z minus fn. And you're going to reparameterize the integral in terms of this parameter u. Now, if you look at that u, essentially, since f of z minus fn is locally quadratic at the saddle point, because f prime is 0, so if you did a local Taylor series expansion of f of z, it will start with terms like z minus zn squared times the second derivative, essentially u is going to have a quadratic local form here. So if you look at it, the u function locally is going to look parabolic of this type, if I plot the u above there. And that then means that it's going to be multi-valued. So there's going to be, if you pick a value of u, essentially there's going to be two values of z that it corresponds to, one on the inward leg of the contour, z minus of u, and one on the outwards leg of the contour, z plus of u. And so you've got to then be careful about that when you do the Jacobian transformation. If you put a u squared in there and integrate from 0 to infinity, it will be okay. But in what follows, this is a useful thing to do. Okay, so when you do that, then what do you get? You do the change of variable from u, you get e to the minus u, because by definition, that's what the exponent was, that's what you're after. And then you get this weird combination in here. What is this? Well, this is just the Jacobian evaluated at the plus point minus the Jacobian evaluated at the minus point. And that's because u is running from 0 to infinity, but the center of the contour is coming in the other way. So that's why that's a minus sign there. So that's what you've done. This actually turns out this is the Borel plane representation. U is the Borel plane, if you like, and this is this will encode all the singularities here, because clearly when f primed is 0, you're going to get blow-ups of the Jacobian, and that will occur obviously at other critical points as well. So the way that we do this is the affectionately known Cauchy sausage contour representation. So basically we take the steepest path here and we surround it with a infinite sausage contour. And I've drawn these as dots because of course they will only connect up at infinity here. So this sausage contour subscript gamma n, nothing to do with the gamma function, but it's just, that's gamma n notation. Then what we can do is we can represent the thing in braces that we had before, this transform complex, this is effectively the Borel transform here, in terms of this contour integral representation. So it's essentially a big loop integral, which can be collapsed down onto these little blue ones if you want, but we keep it as a big loop one because u is going to run from 0 to infinity, and those little blue loop contours add up to that big sausage contour then. And then what you've got is, essentially this is just Cauchy here. So locally this is going to give you an approximation which goes like, if you're away from the critical points, essentially this is then just linear in z minus zn, or z minus the z plus. And then when you do the Cauchy loop integral, this will give you this result here. And then for the z minus, it will give you the minus sign on the other side. This thing with this square root in here looks a bit anomalous to start off with, but that's in there so that actually as z plus and z minus go to 0 and you get these 2 points coalescing, at that point you will change from a linear to a quadratic local form on pole down here. And so you want this to basically still give you a proper consistent uniform representation. So you put that square root in here and then pull it out here, and then everything works out fine. So you take this and you put it into the original integral representation. This is exact. And you end up with, you started with a single integral and now you've got a double integral, which looks like a bit of a crazy thing to do to start off with. But the point then is that what you can do is you have something down here, as Adri has pointed out before, is you can start thinking about expanding this in powers of u. You can pull out this f minus fn below and start expanding in powers of u over k times f minus fn. And that gives you, the point of doing that is that that's exactly the power series expansion, exactly truncated of 1 over 1 minus x, where x equals this parameter here. And so this is going to give you an exact remainder term as well as the series expansion. When you do that and you do all the integrations, you find out that you generate, this is how you can generate the asymptotic terms in the series expansion of this original integral. And so you can do these u over k f and m's give you these coefficients here when you do the integral, which I'll show you in a minute, plus an exact remainder term involving the expression here with u equals k over f minus fn. What are these tn's of r's? Well, they now form just this very nice loop integral. So you've got the gamma of r plus a half over 2 pi I times the little Cauchy loop integral of g of z over f minus fn to the r plus a half. So if you have a relatively well-behaved f of z, and Fn, and you can get Mathematica to work with residues, which it has had a mental wobble over the last couple of years. This is actually something that you can program into and get your coefficients out if you want to. If this integral happens to satisfy a differential equation, of course, it's maybe just easier to get those terms from the differential equation with currents relations, or if it's a discrete equation as well, a difference equation, you can do something similar from that. But if you do the leading order approximation to this, this should be, sorry, T0 down here. If you do T0, then essentially you can come up with what you should know as the leading order of the steepest descent, which is square root of 2 pi over the second derivative times g of z. So that's why you have to be careful with coalescences. It's more complicated when you've got a higher order cubic, when you've got two saddles coalescing, because this is obviously this is going to vanish and blow up then. But there are analogous formulae for higher order critical points as well. So what we're more interested in here, though, is this remainder term, and this is the remainder term that you get. So here is the u to the n over the f of z minus fn times k to the n that we've got from the exact remainder term of that geometric progression. And so we have something which is an integral and another integral. And essentially, this is an exact remainder term. We didn't have historically an exact remainder term from integrals unless you did integration by parts, or you were very lucky to do that. Whereas this is now, this is, albeit a double integral, this is still an exact remainder term. So why are we excited by this at all? Well, the point is, as Adri's shown before with Dingle's converging factors or terminants, you can end up encoding the Stokes phenomenon. And here, whereas the expansions that Adri was doing before were still ultimately divergent, in this case, and for this particular remainder term that we've got, this is actually exact and will incorporate it exactly. So let's now do that work on this a little bit further. We've got a double integral in terms of things which as equally as impenetrable as the original integral, if we thought that was impenetrable. But what we're now going to do is we're going to deform this sausage contour so that it passes through and lies on, it passes through other more distant saddle points, and these aren't going to be all the other saddle points, it's only going to be a subset of them in general. And it's going to pass through certain steepest paths of those other saddle points, which are not necessarily the steepest paths corresponding to the original steepest, the value of theta k that we have here. So how are we going to choose those? Well, before we do that, I'm going to define a couple of things. These are Dingle singulants, as John Chapman mentioned the other day. These are essentially, in the context of saddle point behavior, they're just a difference in saddle height. So FNM is basically the difference in saddle height from saddle N going to saddle M, and this is going to have a modulus and it's going to have a phase. And it's these phases that are going to be important then for what comes following. So in order to select which of the steepest paths I want to deform my sausage contour onto, I'm going to allow theta to vary. And as theta varies, for certain values of those theta, when theta equals minus I sigma nm for a particular saddle point, m, the rotated steepest path through that saddle will intersect the saddle point m. I'll show you in a minute how that works. But it is only those saddles m for which are intersected by varying theta, those are said to be adjacent to n, and it's only those saddles which I'm going to deform the sausage contour through. If I go further than that, I'm going to end up with other singularities coming in, so I'm not going to do that to start off with. And moreover, the paths that I'm going to choose are going to be the paths through the steepest path through Cm, not of the original theta k here, but of the when theta k equals minus sigma nm. This looks all like a bit of black magic at the moment. There's a very natural interpretation in the Borel plane, but I'm doing it because I want to show you some nice animations here. So what I've got here is, again, I'm going back to the Pearcey examples, and I'm going to vary theta k for different cases. So I think this was the case of x, y was, I think, 1, 2, and this was the case for x, y equals 0 and minus 3. And the thing I want to focus on in both cases is what's the adjacent saddles to this particular saddle point here. Okay, so in the first case, it's not too difficult to see. So what the animation you're going to see again is the value of theta k varying, and we'll see the contours rotating. And you'll see that for certain values of theta k, it will intersect the other saddle points. So if I set this one going, I'll let it run through first of all, and you can see that the contours rotate. Let's stop it now and pick it up, and you can see that this is at theta equals 0, and at theta equals 0, whoops, at theta equals 0, if I stop that, you can see that the saddle point, the steepest descent path goes through here first of all, but now it's going to vary, and it's going to vary, and eventually for a thing not so far close to theta equals 0, it will actually connect. You'll see that it connects about here, between there and there, with the steepest path will run directly from this particular saddle point. It hits this one and then goes around there. So that particular saddle, this saddle here, is adjacent to this saddle there. We can carry on around, and you can see that as I go round, the steepest path is bending further, and eventually you won't be surprised to see that at this point it hits this path and then goes off there. And so that saddle is also adjacent. So that in this particular case, the two steepest paths that I will deform to are this particular steepest path, that steepest path when I run from the path from here to here, it connects, and then at 90 degrees it goes from there. And then when I come back to here, you can see that when the connection is happening between these two saddle points, it's going to be these two this steepest path here. And so I'll deform through those particular steepest contours. The direction of which I go through those contours isn't important because it comes out in the wash later on in terms of the sign of the Stokes constant that is associated with it. But essentially, those are for a general case, those would be the steepest paths in that particular case. When I look at the other case, though, something more interesting happens. So in this case, again, the steepest path when I start off is this red line here, passing through this particular saddle. Now, if I want to work out which of the other saddles are adjacent to this particular saddle, I come through here, and you can see that as it goes through, when I get to theta equals pi by 2, there's a definite connectivity between that first saddle and the saddle in the middle. Okay, but there's no, it doesn't, although it might look like it and runs through to the saddle on the right-hand side, we don't push it that far. If we do, we'll end up with other singularities that come in when you do the analysis. So at this point, what we do is, you can see that for any other value, it never actually, there's not a direct connection between the saddle point on the left and the saddle point on the right without having to go through the saddle in the middle. And so essentially what happens there is that we say that this particular saddle point, the saddle point on the left is adjacent to the one in the middle, but it is not adjacent to the one on the right-hand side. And vice versa, if we were to do the same thing for the one on the right-hand side, it would be adjacent to the one in the middle, but not the one on the left-hand side. If we looked at the saddle point in the middle, it would be adjacent to both. So you can see that there's a bit of a one-handedness in terms of adjacency, but that's a nice geometric way in which you can do this for any one-dimensional integral scenario. Later on, I'll show you how to derive that using an algebraic approach. So there we are. We picked which saddles we're going to deform to, and we deform the sausage contours through those, and we pick up the steepest paths here and the steepest paths here. And this saddle here on its own isn't adjacent, so it doesn't get to have the sausage contour deformed through it just yet. So the sausage contour then is basically a topological sum, if you like, over the adjacent saddles. There will be some KNM factors that come in, and that will be for an integral case, in the 1D case, it's either going to be +1 if you choose the contour of the direction of the contour in the same orientation as the traversing of the sausage contour, or it'll be -1 if you choose the other direction. For other more complicated cases in multiple integrals, this can be an integer. For differential equations, this wouldn't be an integer, it could be anything you like. And that's, well, not quite anything you like, it depends on your initial data. And that's usually because you seed the terms of an asymptotic expansion for a differential equation with, say, 1 for the first term, or whatever the initial data is, and then that propagates through. For integrals, there's no ambiguity in what the first term is. it's definitely root 2 pi over f double prime times g. And so that's why this ends up as an integer. If it turns out that these k and m's, as I'll show you later, these are the intersection numbers that you come about in Picard-Lefschetz theory later on. If we deform it further, as I say through here, you will end up initially, to say through this Zn3, you'll end up getting some singularities in the remainder terms. So on each of those CMs, what we now do is, the magic bit is you now make this transformation. So you make this transformation here into, U becomes V, and you rescale it so things are nicely, V is nicely real on that steepest path. And then V can be decomposed into this form here, which is V plus, this is a real number, plus the difference of F from the new saddle point M divided by the difference in heights from where you've come from. So then there's some algebra that you play around with. And at the end of the day, what you end up with is this remainder term. You end up with a remainder term, which is this topological sum over the adjacent saddles of something that, hey ho, this is beginning to look a lot like Dingle's terminant, times remainder times another integral, which looks very much like the integral that you started off with. Okay, and this is in fact what it is, in that you can rewrite this in terms of the original notation, T sub m. This is exactly the rescale version of the integral up to this factor of a half that comes in here, of a new rescaled large parameter V over Fnm, where this bit is definitely looking like Dingle's terminant. So if we put all that together, what have you got? This was the original integral you started off with. You had a truncated series here in terms of expansions in terms of 1 over k to the r. That is then added to with an exact remainder term here, which has got the first part of Dingle's terminant, but is now integrated over this self-similar term, which this integral form here. So this is another example of resurgence. You start off with something on this side, and you end up with it on this side as well. But now this is a contribution from the adjacent saddle points, not just from just from n here. And it's as many adjacent saddle points as you've got. So Adri showed you a bit of an example before in a second order differential equation where you'll have 2, and the area example he did, because area is very similar, the forms of the expansion, the Cauchy-Hein formula gives you area on this side and area on that side. In here, what we've got is this could be, say, the solution of an nth order differential equation, n greater than 1, ordinary differential equation, and this would be one solution, and this would be in terms of the other solutions of the differential equation. So essentially, that's the exact remainder term that we've got, and it's only over certain adjacent saddles. We don't have to worry now any further from dealing with divergent asymptotic expansions. This isn't an approximate equal. This isn't a physicist equal. This isn't a formal equal. This is actually a definite equal sign here. We can now do things to both sides as if we were dealing with the left-hand side. So we can differentiate this. We can differentiate this, which goes beyond Poincaré, and we will get the right results out. So this also can be used to get very, as Andrew's hinted, rigorous and tight error bounds. And that, if you're into those things, that's something that was very useful to do. But also, if you think back to the deformation to the U-plane, this is effectively what we've done here, is we've been working in the Borel plane. I've kept it in the real Z-plane, or in the complex Z-plane for nice geometry, but everything that I've done here can be redone in the Borel plane and for different powers of singularities as well. So in that sense, what I've done here, this remainder term that we've got here is with slight variations, extra complications in powers and things like that. This can actually be used for, at least formally, for solutions of differential equations, PDEs, eigenvalues, and multiple integrals of the type. There's a lot more machinery that you need to do this, but in this is you end up getting relatively similar results. So good result here. We've got an exact result. We don't have to worry about ambiguities. But bad result is that, well, we started off with a 1D integral. We've now got 2D integrals here. We've got this is an integral, and this is an integral that we don't really know. If we don't know this one, we don't know how to do that one. We've also got to work out what these K and M's are. Well, when it's in 1D, it's not too difficult to do. But as we'll see later, when there's multiple integrals and you don't have that nice geometry turning of the contour bit, that gets a little bit more complicated. And so those are the three bad things that we've got going on here. So why do we bother with this result? Well, this, as we'll see, introduces, I apologize for this, this introduces this term down here, which is going to give us all the Stokes phenomena at the same that we want. So first thing is just to show where the late term behavior, as Adri hinted, comes in. So you can get it from differential equations and differentiation and things like this, or in this case what you can do is you can essentially take your exact remainder terms, you take n, capital N, your truncation to n plus 1, so you get this is the sum, you change all the n's to n plus 1s in this exact remainder term, and this is still true. So this hasn't changed on the left hand side, the only thing that's changed is on the right hand side. So if you subtract the second line from the first line, you get a big 0 on this side. This term, all these terms cancel except for the one that you've just pulled out, the Tn, capital N, and then these subtract, and after a little bit of algebraic simplification, you get this form here. Take this on the other side and kill off the powers of k to the n, and so this gives you then, this will give you another exact representation of the for the terms in the saddle point expansion about n for November, in terms of the saddles around m for Mike, the sum over all of them. And then, again, we don't know what this is, but let's substitute the asymptotic expansion for this in. When we do that, it's of this form, and it's of this form, and then you get this result here, which, as you swap the integral and the sum around, and what do you end up with? Well, you end up with a factorial over power form times the early terms in the distant saddles, now with a topological sum over them in terms of the contributing saddles. And you can ignore the fact that S is greater than N here. This is the naughty thing. In this particular case, when you have simple saddles, this is another extra complication. But essentially, leading order, it's factorial over a power times the first term in the more distant expansion here, the adjacent saddle. The dominant form will be the smallest mod FNM here. That will dominate as n goes to infinity and be the largest series, the largest contribution, and so that will give you your factorial over power. However, in general, the formal asymptotic expansion will involve all these other contributions as well. For other types of expansions, when you've got endpoint expansions or other more general cases, you'll have a fractional thing in here or other terms, which will mean that these gamma functions don't blow up, and that's fine.
Chris?
Yeah.
I think it's time to stop.
Okay. All right. How many more slides have I got? Hang on a minute. Yeah. I've got a couple more slides if I can do that, please, and then I'll finish.
It's 1 minute past 4.
Yeah. But this is the crux here. So how does this do the Stokes phenomenon? It does the Stokes phenomenon if we go back to this exact remainder term here, and as Adri has seen before, essentially as theta k sweeps through one of the values of minus sigma nm, as we've seen, is when you get that connection between the saddle point n and the saddle point m. Essentially, you get that connection. This KFNM here, down in its bottom here, becomes real and positive. So you've got a pole. So essentially, what happens is at that point, when you get that dogleg curve like this between n and m, what happens is that you're effectively picking up the pole in the contour of integration, the v. It comes along and it snags, and then it goes further, and you get a residue contribution. The residue contribution then that you get is essentially very easy to work out. It's just where v equals k over FNM, and that then generates this expression here. And so that says that the Tn, the saddle point contribution, or saddle point integral expansion through n, just for k less than the on the other side of the just before the Stokes phenomenon, compared with what it is after it. The difference between it is this exponentially small contribution here, which is you've got the Stokes constant, you've got the exponentially small term here, which is coming in, and then this new saddle point expression here, which will be this full contour through n that you get if you go a little bit further. So essentially, that exactly incorporates the Stokes phenomenon. If you like this, then you can make this is what happens as you cross it. But it will pick it up exactly, and there's no asymptotics here. It's just an exact representation that you get these extra contributions from Tn. Just one final slide, as Adri's hinted, is that if you look, there are some. If you go for arbitrary higher order contributions with saddles and various other combinations, you can get again very tight error bounds if that's what you're interested in here. And this, I think, is for as Gergo derived in 2018, and he'll talk more about that later on. So computations of the coefficients, some practical issues that we've got there. And so yes, if you can compute those coefficients, everything is fine. If you can't compute them, then it's a little bit more complicated. You've got an exact result, but it's implicit. You need to know what those TNs are to calculate the TNs. That looks like a problem as well. If you calculate with the critical points are adjacent, you need to work that out. You need to know what those KNMs are. So you have to worry about how that happens. Geometrically in 1D you can do that. In higher dimensions it's more complicated. And so you can't do this. But there are several other methods available for doing this, and I'll illustrate one next time. I should say that as well, there are other ways of doing it geometrically. So for example, using Borel-Laplace and things like that. But this is the way that I'm going to use in this example. And I think here's an example of generalizations. It does finite contours, Borel plane PDEs, and all of that lot. Those are there for you to look at when you wish. But I think that is where I want to get to today. Thank you very much. Sorry.
Thank you very much, Chris. There's some questions on the chat. Perhaps we should answer them, or some of them we can answer in writing. Before we start with Gerald, we are already behind schedule. The first one is goes back to your slides on page 77, the page numbered at the top. Do you know of any finite dimensional integral example? Sorry, not this one. Are the paths not connecting any saddle, just Mathematica numerics?
Yes, that's just Mathematica problems. I did this using contour plots rather than just solving the flow equations. And so if you ask for the contours of a certain value, then it picks up the stray ones there. So yes, those are naughty.
Another question, do you know of any finite dimensional integral example where the intersection numbers K and M are rational rather than integers?
It may be possible to get when you've got singularities in F, but I don't have an immediate one to hand. The way that it works for the simple cases that I've looked at here, these are all with nice real analytic F, and so it can either connect or not connect. But if you start introducing singularity into it, if you look at K0 Bessel functions and things like that, you can get double integer values and things like this. But so it may be possible if you've got branch cuts in F as well, that you can get these weird things happening.
Thank you. Next question. In common parlance, adjacency is a symmetrical relation. Same here for saddles? For simple saddles, adjacents, for simple saddles in one-dimensional cases or without boundaries, adjacency is reciprocal. So if something is adjacent to one, if one is adjacent to two, two is adjacent to one. But as we'll show tomorrow, that doesn't hold and breaks when it comes to when you put boundaries in. Then things change, and so you can have one-way adjacency. Okay, two more questions. Another one, in this construction, referring to your last slide, in this construction, is it correct to get the idea that each of these saddle points that you can pick up when deforming the sausage contour gives a contribution with a different exponential level or layer in the asymptotics?
Yeah, so each of the adjacent saddles will give you a different exponential contribution. Well, it will give you a different exponential contribution from the one you first started with. Of course, they could be the same if you've got symmetries going on in your function, so that the two adjacent ones could give you this a doubling up or an interference of an exponential contribution as well. And so I think later in the talks I do mention that you can have, when you have that going on, you can have that leads to oscillatory behavior, modified behavior in the factorial over power. You don't have a pure factorial over power. You end up with oscillations going in, coming in as well, because there's cancellations going on between terms.
And one last question, are the methods discussed today restricted to ARAW01 asymptotics?
No, I believe yeah, they're not. You can do it for other types of Gevrey as well. Okay.
So that's all for now. Thank you, Chris, and let's thank you with a visual. Right. Oh, we can't use reactions. Anyway, thank you very much, and thank you, Adri, as well. And now I think it's time.